Okay, everybody, this is the beginning of review problems for chapter 15. I'm just going to start picking problems from homework, probably, or making up some problems. This is a 15.48 star problem from the homework. We have two masses attached by a spring on a frictionless surface. It's horizontal. We know the spring constant. We know the masses. They are not equal. We're going to pull them apart from each other 2 meters from its equilibrium position and then release them. And we want to know basically how fast they're going to go, because that maximum speed is going to occur when it is at its unstretched position or the spring is at its equilibrium position. And then the restoring force will push them back in the opposite direction. So we want to know when it has no more stretch on it. It's not being compressed yet, but it's not being stretched anymore. Don't need to know any distances other than the fact that it's stretched 2 meters, and let's go ahead and conserve momentum. For the system, we have the conservation of momentum to start is equal to the total momentum after. Alright, well, let's do that for each object. We have some mass A times the velocity of A initial plus mass B times the velocity of B initial is equal to, they are attached, but they move separately with different velocities, so let's keep it that way. Mass A times the velocity of A final, or at 2. I guess I should have done 1, and 2. Yep, there we go. Plus mass B times the velocity of B at 2. Alright, what does this give us? Well, they're initially at rest, so we get a big 0 is equal to, we know the masses. The first mass is 40, and we'll call that the velocity A at 2. And we know mass B is 60, and just keep it multiplied by the velocity of B at 2. This is our equation number 1. We now have a relationship between how A is moving with respect to B, but that doesn't give us enough information. We still have 2 unknowns. Let's conserve energy. Let's say T1 plus V1 is equal to T2 plus V2. Does it have any kinetic energy to start with? Is it moving? Well, it's stated in the problem it was released from rest. So let's put a 0 through there. And it's asking for the speed when the spring is unstretched. So we have no potential term for the spring, and we're not dealing with gravitational potential or any other type of potential. We can cross that one out. So I just get a 1/2 kx squared, and that's all going to turn into a 1/2 mva at 2 squared plus a 1/2 mvb at 2 squared. What do we know? We know that this stretch is 2 meters. We know the masses. We know K. We do not know these, but we have another equation. So let's call that equation 2 using equation 1 and substituting into equation 2 however you would like. 1 into 2 will give me a velocity for A with a magnitude of 3.29 meters per second, and the magnitude of the velocity of B as 2.19 meters per second. Alright, kind of fun problem. What's actually interesting too is if these are frictionless, imagine this just sliding over ice or something, it's going to oscillate about the mass center. And if they were equal mass, that would be right down the middle. And they would just oscillate with the same speed actually in that case too. The masses are what determined the fact that we had different speeds for each. Each one has a different mass. The force is the same though applied on it, and it's going to accelerate relative to that force. But if we have one mass bigger, like we did, or sorry, one mass heavy, that is a larger mass than the other side, it's going to skew that mass center over to the right a little bit. And so everything is going to oscillate back and forth about that new mass center. The whole thing could be sliding with some velocity also, right? Let's not talk about making it rotate just yet. Alright, thank you.